Okay, hi. This is the first video lecture for linear algebra, Math 130.1. This is corresponds to chapter 1.1 in Professor Strang's book. You might know a lot of this already, so we'll just go through it on the video lecture. So first topic is just vectors, and you'll see soon that vectors have a more general definition, which is important. But we're going to start with just certain types of vectors, which are vectors in Rn. So the key distinguishing feature of these is that they're just an ordered set of numbers, and they're usually written like this, in parentheses stacked on top. Here I say an n because n can be an integer, positive integer. This is an example of a vector in R2, okay, if v1 and v2 are real numbers. So can you give me an example? So example, you could have w equals 1, 3, 7. That's my pin number? No, I'm just kidding. So that is a vector in R3. And they have to be in this order. In other words, if u is something else, if u is 3, 1, 7, u is not equal to w. Okay, so we have a couple operations. The two most important operations, certainly for us, are scalar multiplication and addition. So we have operations on these. So suppose we also have u equal 0 minus 2. It could be pi. Just as long as it's a real number, it's in R3. Okay, so that's also in R3. So we have u plus w is equal to, I just add the corresponding entries, right? So this is just equal to 1, 1, 11. Okay, so addition. We just add. So v is in Rn. Say u and v are in Rn. Then u plus v is equal to the vector u1 plus v1 dot 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 un plus vn. Okay? Okay, good. Scalar multiplication, even simpler. We just multiply every element of the vector by the scalar value, which is just a real number for now. So we could have scalar multiplication. So say we want cu would just equal, say, if u is in Rn, cu is just equal to cu1 dot 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 cun. Okay, so if, for example, suppose we have 5 times 0 minus 2, 4. This is equal to 0 minus 10, 20, right? Just multiply each. Okay, by far the most important thing we'll do with vectors are multiply by numbers and add. And especially we'll do that together. So that's called a linear combination. So let's define this. Linear combination or linear combo is just on two vectors or more than two vectors is a sum of scalar multiples of vectors. So linear combination of vectors is a sum of scalar multiples of them. I'm not going to be able to write. I'm going to be starting to abbreviate as we go, you'll see, but for now we're good. So we can also represent vectors graphically, and let's demonstrate a linear combination graphically. So typically, since they're ordered, a nice way to represent them is with an arrow. So we can represent your vector. We can represent V, say, equal to, let's just do it 1 in R2. Actually, it gets harder once you're out of R2, right? 1, 3. On, say, just the coordinate axes with at right angles like this. Usually we'll think of this as the second coordinate, you know, sort of like you're used to graphing things. This would be the vertical, on the vertical axis. So 1, 3, 3 up, 1 over, right? Something like this. Okay, so this is V. Okay? All right, and this point here corresponds to the point 1, 3 in the plane. And that's a good time to know. We'll also represent vectors. This point is 1, 3. We'll also sometimes write vectors like this, just so we don't have to have these long things if we're going across. Like, we'll write it like this. It's the same thing. I have to put the comma there, though. It's something else if I don't put the comma. So this is just a notation point, okay? All right, so that's good. So let's look at a linear combination. So suppose I have V is 1, 3, and let's make W, say, equal -2, -2. And let's look at, I don't know, let's just start with maybe V plus W. So V plus W is equal to, I just add corresponding entries, right? -1, 1. And we could do this like this as follows, because, okay, so for V, I'm going over 1 and up 3. Right, 3 and 1. So now W says take 2 away from this one. That puts me over here at -1. And take 2 away from this one, that puts me at +1, right? So I know already that the solution is this. These aren't at right angles, are they? No. Okay, doesn't look that way. Okay, so it's something like that. Problem is I didn't make 3 high enough, so it looks a little bit like a right angle, but it's not. It's acute. Okay, so this is V plus W here. That's not a vector, it's just a pointer showing you. And this is V. And where's W? -2, -2. So one thing I could do, -2, -2 looks like this. Right, something like that. Should be a little further past that. And I can, sorry, that's not right. That's 2, sorry. It's like this. That's 2 -2, right? It's like that. So you can see if you translate this here and look at it as subtracting it from that point, I end up from starting at V, I add W to it, which is going this way, and I end up at my result, V plus W. Let's do an easier one. Example 2, that was too hard. And okay, so example 2, so suppose we have V equals 2, 0, and W equals, these are vectors, I don't know, -1, 2. This should be, even I should be able to do this. So let's not compute the answer until we do the graph. So 2, 0, right here, right? Something like that. Now, so those are my units there. So now, I do the next, okay, so I do the addition. So what's W look like? -1, but +2. So W looks like something like this, right? -1, 2. So now if I start here and do that, I should end up at the right place, right? So I'm gonna like take a parallel line here and just make a W there. And you see it ends up at the right place. This vector here, that vector is equal to the sum, V plus W. So that's equal to 1, 2. Okay, and this is W minus 1, 2, and this is V, 2, 0. So we can add them like that. It makes sense. You're just altering each coordinate all at the same time, kind of, when you do that. I can't do it in 3 dimensions even. It's too hard to do, unless you're a very good artist maybe could do it. But I don't try usually. I won't ask you to either, but you should understand this is what's happening. And even if it's in R4, it's the same thing that's happening. You just can't represent it. You can't see it 4 dimensions usually, unless you are dreaming or something, and then maybe you can see it, but you can't see it normally. So, all right. All right, these videos are going to be pretty short, and there'll be a lot of them. One reason is YouTube doesn't like you to put long videos up. So, so these are just sums. I can do a linear combination too, just much the same way. So maybe we should do this, and then we'll get to the main point in the next lecture. Okay, of all this. Well, I guess it's the main point. So let's maybe do a linear combination. So suppose we have another example. Say V equals, I don't know, 1, 0, and have W be, say, 2, 1. And let's have V, or W, say, plus 2V. Well, I just follow the rules, right? This is just 2, 1, plus 2 times 1, 0. That's 2 zeros, so I get 4, 1. And we could do the same trick graphically. I think this is pretty similar to what we had last time. So 1, 0, so this is V. I double it, I get 2V, and now I add W to it. W is a little different this time. It's 2 over and 1 up. Right, so I add that. That's my W, and I end up with my linear combination. So that's my LC. It's 4, 1. This is W plus 2V. Okay, very good. All right, believe it or not, the video's over. Please check out the second video now to see where we're going.